Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and Python files and understand them yourself and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding and they just need little hints for implementation from scratch. In this video, I'll explain and implement the estimation of survival functions. What are survival function and why do we need them? I'll explain it, and we'll specifically talk about Kaplan Meier estimates. So in survival function, we have time to event data where we want to estimate the event given the time. So we want to estimate that function. Let's jump to the workbook, let's jump to the whiteboard and the notebook to understand the idea and implement it in Python. Okay, so in survival analysis, we have time to event data. Time to event data looks like this table. So where we have time for each of our patient, this could be patient or any item or anything for which we want to estimate this event given the time. So this could be a machine which is working for some time and we want to estimate for another machine given some time whether it will fail or not in a couple of years. So in this data we have patients of patient number 0, 1, 2, 3. This is like patient ID, and depending on what kind of patient it is, whether it is a cancer patient or it has some so it is like grouped into different groups. It is for our own analysis, it is specific to this domain. It is again just for comparison of different groups in time to event data. We'll look at it in the notebook in detail, but the important part is this time and event. What does it show? It shows that patient 0 has lived up to 6 years, but after 6 years this patient has died because the event was observed. So event 1 means that the event was observed, or in other case the patient actually died. So if in the case of machinery, so we could say that the machine worked for 6 years, but after 6 years that machine stopped working. So for patient number 1, which is coming from group 1, has survived up to year 19, but it stopped it stopped breathing, and this patient actually died after 19 years. So this happens for all of the patients. So we store this information for each of the patient. But what happens when we have missing data for some of the patients? Suppose we have a patient 5 which lived up to 20 years but did not come for survey after 20 years. So we do not know whether that patient survived later after 3 years, in the age of 30, whether he was alive or not. So we do not know the details. So this is what we call a missing data. So the missing data will be stored by the value of 0. So this is also termed as censorship. So because we don't have information regarding this patient or this item. So this is how the data is. So the important columns are time and the event. For anything, that anything could be person, that anything could be item, that anything could be anything. So what we want to estimate is that given the time for that anything, that could be patient, that could be item, that could be machine, given the time, we want to estimate whether that thing will be alive or in working condition till that time or not. So whether that event will be 1 or not. So this is our main task in this whole survival analysis, or in this whole video, where we want to estimate this survival function. That is why it is called a survival function. So we want to estimate the survival of a thing. That thing, call it patient in this example. We want to estimate the survival of a patient given time. So time is in input, this is input, and event is in output. So this is not a simple classification problem. You might think of that as a classification problem, but this is not a classification problem. Okay, so this is a completely different set of a problem. That is why it is called survival analysis. Okay, one of the way, so let me just clear the mathematical notation. So this is S of t, where we want to estimate the survival function given this time, and we want to find out the probability of the patient survived past time t. So if I'm asked that what is the probability of patient to survive past time 25, so what is the probability that this patient will live at least up to 25? It will live even after 25 years. So this is what I want to estimate. So this is the notation. We want to find out this probability. One of the easiest way, or the simpler way, or the naive way of estimating this function is simply finding out the number of patients who survived past time t So how many patients are there who have lived even after 25 years? So if in the input we are given the time of 25 years, so how many patients have lived even after 25 years? Once we know that, we divide it by the total number of patients who were not censored before time t, and how many patients were there who actually died before time t, before 25 years. So this is in a way of a naive way of estimation. The problem here is that it do not take into consideration the censorship values. So if we have a lot of censored values, so it will never work good, or it will never work better in places where in places where there are censored values. And we will look at the example, and we will compare it with this Kaplan Meier estimate. And this Kaplan Meier estimator really works great even if there is censored data. So we will compare it. Okay, so what is the formula for that? The formula for finding out this Kaplan Meier estimate is very simple. 1 minus d of I divided by n of I, where I represent the time ti less than equal to t, and we multiply, we take a product of these terms. What do I mean by that? So consider if I have to estimate the survival time past 25 years. So I have to find out 1 minus, where the time will be 25, 24, 25, 24, ti will be 25, then 24, 23, 22, 21, 20, up to 0. So for each of I, for 25 it will be 1 minus d of 25 divided by n of 25. For a 20 ti equal to 24, this d of I will be d of 24 divided by n of 24. So if I expand this function, basically this is 1 minus d of 25 divided by n of 25 multiplied by 1 minus d of 24 divided by n of 24, and this thing will go on again and again up to 1 minus d of 23 by n of 23 up to 1 minus d of 0 divided by n of 0. So this is how it goes. And what does it mean? Basically it means di represents number of deaths at time I, and n of I represents number of people who we know have survived up to time I. And calculation of that is really simple. This is a simple 2-line code. Okay, once we know that, then we take a product and find out this whole thing. Now the actual problem is finding out how this formula actually came into being. As I have already explained, this is implementation part, so I will just go through it very roughly and very fastly, so you can have a detail of it. And there are a lot of articles and books on survival analysis where you could find this whole topic of Kaplan Meier estimates and the derivation of it. So the main idea is that we want to find out the survival past time t, and we can write this past time t like that. We want to find out the probability that capital T is greater than 25, so that the patient will survive past time t. What is the probability? Okay, we can also write this greater than t is equal to, basically the years are in discrete form, so whether it will be 25 or 26 or 27. So this term is equivalent to this below term, where probability of t greater than equal to 26 also represents this same thing, the survival of patient past time t, past 25 years. So if it is greater than equal to 26, then we could write this probability in this form. Why? Because if patient the probability of patient past surviving 25 years means that it is the probability of past surviving 25 years and 24 years and 23 and 22 and go on up to 0. This is how it came into being. Then by using the chain rule of probability, this whole function can be written in this form: probability of t greater than or equal to 26 given t greater than or equal to 25, and probability of t greater than or equal to 25 given that t greater than or equal to 24. In the same way, the whole product goes up to probability of t greater than or equal to 0, which is equal to 1. If you don't write it, it's okay. Okay, now what does this individual term actually represent? This can be written as probability of t greater than 25. These both terms are actually interchangeable, as I have already explained here. This t greater than 25 and greater than equal to 25 is representing the same thing. So we have written it again in the previous form. Given t greater than equal to 25, this simply is actually 1 minus probability of t equal to 25. So this is like probability of living past 25 years. This is like probability of dying at 25 years. That's why we have used this 1 minus probability sign, because they both are then same. The total probability is equal to 1. So once we have the once we have this living probability of past 25 years, then we can say that 1 minus probability of t equal to 25 is actually the same thing. Okay, once we have this thing, then this is actually a way of this formula, and this product is actually done because we have all these other terms in the product. Okay, if you have understood this mathematical formulation, perfect. If you have not understood it and you are still confused, go and look at this Kaplan Meier estimates and write it out in Google page. You can find out a lot of explanation for that. Okay, once we have this formula, this whole explanation, this whole understanding, we have to just apply it. I'll apply that, and you will see that Kaplan Meier estimates actually deals with this missing data very effectively in comparison to this naive estimate. I hope so this is clear. Let me jump to the notebook. Okay, so we actually import the libraries. This Lifelines library also contains this Kaplan Meier fitter, but we will implement it from scratch. Okay, so we will load the data. Once we loaded the data, this is the form where we have different patients, and these are all of these patients are coming from different groups. Group 1 is actually representing a separate group. Group 2 is of a different patient types. Okay, so for each of the patient we have this time and event data. Then we look at the sensor data. So for each of the in this table, we have this event equal to 0 for each of the patient for which we do not have information and for which the data is actually censored, so we do not know what happened to that patient. So we want to find out fraction of those patients. Once we find out using this formula where the event is equal to 0, we sum it and we then divide it by the total length of data frame. We then look at the fraction, which is 32%, about 32.5%, and we plot it. So after plotting, we look that so it is really observed that the sensor data, basically the lot of sensor data is in this range of time, where the time reaches up to greater than 250. So there are a lot of patients for which the data is basically censored. So this range is very important, between 250 and 350. Okay, so this is the survival estimate that we want to estimate. This is a naive estimator. As I've already explained, we want to find out we want to find out the survival function using this data frame, and data frame contains the event time and event data, and the time will be given as an input for which we want to find out the estimate. So this is the formula that I had explained. This is the encoding of that formula. Once we have done that, then this is just a test cases to see if our implementation is right or not. Okay, once we have done that, we have plotted it for time from 0 to 350. Okay, next what we do is we use Kaplan Meier estimates using this formula, and this formula is quite simple, where when the event time is 0, the probability of survival is 100%. Okay, after that, then what we do is we look at the unique times, that are available in our data set. We sort that, and for each of the unique time, what we are interested in is the compute number of people who survived at least to that time, which is n of t, and compute the number of people who actually died at that time, t. So once we have that, then we simply put it in this formula, and this is how this Kaplan Meier estimate actually works. So this is basically a 3-line of code. This is really easy if you look at it. Okay, once we have done it, these are again test cases just for checking whether our implementation is right or not. Okay, then again we apply Kaplan Meier estimate and look at this range from 250 to 350. This naive estimation is saying that the survival is very less for these 250 to 300 estimates. Why? Because there are a lot of sensor data. So once data is not available, so the survival function is affected by that. But Kaplan Meier estimate is not affected by that fact in the range of 250 and 350. So this is really great. Now this is a subgroup analysis where we first of all extract the data separately for each of the group, and for each of the groups separately we fit the Kaplan Meier estimate, but this time we use the internal function of Lifelines library, and we compare it, and these so it shows that the stage 3 patients are not that much dangerous, and there are more survival probability for stage 3 cancers, for stage 3 patients. However, for stage 4 patients are really dangerous, and there is a less chance and less probability of their survival. So maybe maybe doctors must attend stage 4 patients very urgently on the urgent basis. Okay, so then this is log rank test. This is also given by the Lifelines library, where this test is used to compare two functions, two distributions. Okay, I think so the main task that we wanted to achieve was to find out the Kaplan Meier estimates, and this is done in these few lines of code. And the formula 1 minus dn by ni is di by ni is actually very simple to implement, but if you understand the intuition behind it, then I mean you have already done a very good deal of survival analysis.